Hey everyone, it's Ken. Today I want to talk to you about the substitution rule for definite integration. So what does it mean? What's the reason why it's true? And can we do an example that kind of ties it all together? So let's just dive right in. So here's the example that I like to do. So suppose that you're on a test and you see the following problem. So this is what we've got. So let's say we're looking at the integral from 0 to the square root of pi, and you've got maybe cosine of x squared times 2x dx. And you look at this and you say, I don't know what to do. I mean, well, you sort of know what to do because you know integration pretty well already. You know that you want to find an antiderivative of your integrand and then evaluate that from like b minus a. But the question is, how do you find an antiderivative of cosine x squared times 2x? How do you find a function whose derivative is equal to cosine x squared times 2x? But then you notice that your friend on their test has the following problem. All they have to do is they're looking at the integral from 0 to pi of cosine of y dy. So you look at your friend's paper. Not really, but you look at your friend's paper and you say, wait a second, like how come that problem is so much easier? Because you know how to do this one. You can say the antiderivative of cosine is actually equal to what? It's equal to sine, right? So when I do this, I'm going to get sine and then evaluate that at pi and then evaluate that at 0. And so sine of pi is equal to 0, sine of 0 is equal to 0. So the answer is going to be equal to 0. How do you conceptualize that? Well, half the area is above the curve and below the x-axis. The other half is below the curve and above the x-axis. They cancel out to give you 0 signed area. And so how come that problem is so much easier? Well, it turns out that actually these two integrals are the same. They're both equal to 0, and the reason is because of the substitution rule for definite integrals. And let me explain why. So how are these two things related? So here you've got cosine of x squared, and here you've got cosine of y. And so that makes me think, well, the thing that relates them is really this equation that y is equal to x squared. So mathematicians will also sometimes call this a change of variable. Here you've got variable x, and here you're going to have variable y. So notice something else. So look at these bounds of integration. You're going from 0 to square root of pi. That means your variable x is going from 0 to the square root of pi. So what's your variable y doing? Your variable y is going from 0 squared equals 0 to pi, which is the square root of pi squared. So you've got one interval over here for your x values and one interval over there for your y values. But the thing that's kind of confusing, or at least it was confusing to me when I first saw this so many years ago, was, look, what about the 2 times x dx? So why shouldn't it just be true that cosine x squared is the same thing as like the integral of cosine y if you just say that y is equal to x squared and do that change of variable? So in order to conceptualize that, or to suss that out, you need to think for a minute about what is the definite integral really. So if you remember from our lesson on defining the definite integral, this is supposed to be the signed area of the curve. It's the area below the curve minus the area, or the area below the curve minus the area above the curve and below the x-axis. And you get that signed area by taking an approximation by rectangles, what we call a Riemann sum. And so that would look something like this. Using summation notation here, you would take, maybe you chop up your interval from 0 to square root of pi into n little subintervals and go like x0 up to xn equals square root of pi. So you plug in like cosine of xi squared, and then you take 2 times xi, and then you take that's the height of the rectangle, and so instead of dx you have delta x representing the width or the width of the interval from xi minus 1 to xi. So this is actually your approximate area, and then you add that up, of course. I goes from 1 to n, and then you'll take the limit as n goes to infinity. And when you take the limit of those approximations, then it becomes the integral. Same way over here, this is going to be like a limit as n goes to infinity of some approximate area. And in this case, it's just cosine of yi. I goes from 1 to n, and then you've got delta y. And so the assertion of the substitution rule is to say that like these two limits are definitely the same. And the way I'm going to give you to indicate that that's going to be the case is to compare the two terms. You know, here you've got cosine xi squared times 2xi delta x, and here you've got cosine yi times delta y. And it turns out that each of these terms are going to be quite close together. And when you take the limit, when you let n goes to infinity, they're not just going to be close together, they'll be exactly equal. So first of all, you've got y equals x squared. So cosine xi squared, that's just going to be cosine of yi, because xi squared equals yi. So what about like this? So what about comparing delta y and 2xi times delta x? So how do we compare those? How do we get a relationship? And the thing I want you to think about is that this is really an interval for your x values, and this is really an interval for your y values. So if you look at some small change in y, like yi minus 1, how can you represent that as a change in x? So you've seen this before when we did linearization. You learned that actually a change in y is going to be roughly equal to take the derivative of function y, or in this case, y equals f of x equals the integrand. Take the derivative at some point, and the point you're going to be looking at in this case is xi, and then times delta x. So you've got this change in y, and that's going to be roughly equal to the change in x multiplied by the derivative at whatever point you're at. You're at xi. Well, this is great, because the derivative of x squared, that's equal to 2x, plug in xi, multiply that by delta x, that's roughly going to be equal to delta y. And that's just the statement of the fact that when you change variable from just some interval of x values to an interval of y values, but those y values are related to the x values by x squared, then if you change the y values by some amount, that's not changing the x values by the same amount. It's changing them by x values times the derivative, because that's what derivative does. It tells us the factor by which we're stretching out when we're doing like a small change. So that's great. So what this is roughly equal to is it's roughly equal to this sum, I goes from 1 to n, of cosine of yi times delta y. And if we were doing an analysis class, if we had the precise definition of the limit, those so-called epsilon delta arguments, whatever, then I could argue precisely, yes, there's a little bit more to it, but this is definitely the idea. And this approximate equality becomes equality when you take that limit as n goes to infinity. And then what are you left with here? You've got nothing but the integral cosine y dy. So that's a long argument that tells you why these things are definitely the same, but I also want to give you a way to start with this and efficiently calculate that this is going to be the answer without having to go through this process the whole time, because you don't want to go through this process all the time. I'll wipe down the board and do another video to show you how to do that cleanly and maybe give you a couple more examples.